Like ammonia, amines are also basic in nature. Their basic nature is due to the presence of a lone pair of electrons on the nitrogen atom. This lone pair of electrons is donated to the proton of an acid to form a new bond. Amines are weak bases as they combine with water to produce fewer hydroxyl ions per unit volume. For example, an alkanamine combines with water to produce hydroxyl ions, as shown in the equation here. By applying the law of mass action to the equation, the base dissociation constant or basicity constant Kb equal to the product of molar concentrations of RNH3+ and OH- divided by RNH2. You get an idea of the relative basic strength of amines from their Kb or pKb values. The larger the value of Kb or smaller the value of pKb, the stronger is the base. By observing the pKb values listed in the table, we can say that aliphatic amines are stronger bases than ammonia. On the other hand, aromatic amines are weaker bases than ammonia. The Kb or pKb values of amines are affected by factors like the inductive effect of the groups present in amines, the ease of solvation of protonated amines, and steric hindrance. Consider the inductive effect of an alkyl group of an alkyl amine. Since it tends to donate electrons, an alkyl group R pushes electrons towards the nitrogen atom and thus makes the lone pair of electrons more available to the proton of the acid. Moreover, the alkyl ammonium ion formed from the amine is stabilized due to the dispersal of positive charge by the plus inductive effect of alkyl groups. Hence, alkyl amines are stronger bases than ammonia. Thus, the basic nature of aliphatic amines increases with an increase in the number of alkyl groups. Therefore, the basicity order of aliphatic amines in its gaseous phase is tertiary amine is greater than secondary amine is greater than primary amine is greater than ammonia. On the other hand, the basicity order of aliphatic amines in its aqueous phase is ammonia is greater than primary amine, is greater than secondary amine, is greater than tertiary amine. This can be illustrated on the basis of the ease of solvation of cation. The positive charge on the nitrogen atom is also stabilized by the effect of solvation in aqueous phase. The smaller the size of the ion, the greater will be the solvation with water molecules and more stabilized will be the ion. Thus, the order of basicity of amines in its aqueous phase is exactly opposite to the order based on inductive effect. Another important factor that affects the order of basicity is steric hindrance. If the size of the alkyl group is small, like the methyl group, then there is no steric hindrance to hydrogen bonding in its aqueous phase. If the size of the alkyl group is larger than the methyl group, then there is steric hindrance to hydrogen bonding in its aqueous phase. As the size of the alkyl group increases, the steric hindrance to hydrogen bonding increases, and the basicity decreases. Thus, the relatively basic strength of primary, secondary, and tertiary aliphatic amines is due to the combination of inductive effect, solvation, and steric hindrance. Now let us consider the order of basic strengths of aromatic amines. By observation, the pKb values of aromatic amines are quite high. This can be explained on the basis of the resonance stability of aryl amines and aryl ammonium ions by taking the example of aniline or aryl amine. The NH2 group in aniline or aryl amine is directly attached to an aromatic nucleus. As a result, a lone pair of electrons on the nitrogen atom is in conjugation with the aromatic ring, thus making it less available for protonation. On the other hand, the protonated aniline or anilinium ion obtained by accepting a proton can have fewer resonance structures than aniline. You know that greater the number of resonance structures, greater is the stability. Thus, aniline is more stable than the anilinium ion. Hence, the proton acceptability or basic nature of aniline or other aromatic amines would be less than ammonia. In case of substituted aryl amines, electron-donating groups such as methyl, ethyl, and methoxy increase the basic strength, whereas electron-withdrawing groups like NO2, X, SO3H, COOH decrease the basic strength. Here's a problem for you to try. Arrange the given amines in descending order of their basic strengths. Try to work out the answer yourself before checking the solution. The descending order of basic strengths of the amines and ammonia is dimethyl amine is greater than ethyl amine is greater than ammonia. This is explained on the basis of plus L effect of the alkyl groups. More is the number of alkyl groups, more will be the plus I effect. Here's another problem. Arrange the given amines in ascending order of their basic strengths. Try to work out the answer yourself before checking the solution. The ascending order of the basic strengths of these amines and ammonia is: paratoluidine is greater than aniline is greater than p-nitroaniline. Here, NO2 has a minus I effect and is thus less basic than aniline, while methyl group has a plus I effect and is therefore more basic than aniline.